Section 5.2, definite integrals. In the previous section, we were looking at Riemann sums as a way to estimate the area underneath curves or between curves and the x-axis. And we talked about those Riemann sums as just being approximations for the area. And we said that the way to make the error go away was to take the limit as the number of rectangles goes to infinity. When we do that, we are creating what's called the definite integral. So let f of x be a function that is integrable on the closed interval from a to b. Then the definite integral of f on the interval from a to b is denoted by, and we read this as the integral from a to b of f of x dx. That is the limit of the Riemann sum as delta x becomes small. And what makes delta x become small is the number of rectangles goes to infinity, or as n goes to infinity. So the definite integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum as k goes from 1 to n of the function evaluated at x sub k times delta x. So they use this word integrable up here. So what does that mean? We have a definition below. If f is continuous on the closed interval from a to b, then it's integrable. Or if it's bounded on a to b, so it doesn't go up to infinity or negative infinity with a finite number of discontinuities, then it's still integrable on a to b. Most of the functions that we're going to find the definite integral for are continuous on the closed interval, so the other thing about the discontinuities won't be an issue too much. Notice, though, that it has to be bounded, and what that means is you can't have vertical asymptotes where the function's going up to infinity or down to negative infinity. All right, just to get used to the notation, let's look at this first example. They want us to write the limit as n goes to infinity of the sum as I goes from 1 to n of sine squared 2 pi xi star delta x as an integral, assuming that the interval we're working with is from 0 to 1. So a few things. First of all, it doesn't matter that they're using an I instead of a K. So if we look here, they're talking about I and I. So whereas up here, it's K and K. That's really just a placeholder, so it could be any letter. So I just wanted you to get exposed to the idea that that letter is not always the same every time. So that's no big deal. It doesn't affect what we're doing. All right, so now seeing how the pieces fit together, this part right here, the limit as n goes to infinity of the sum as k goes from 1 to n, I think of that as becoming our integral symbol. And then we have the function inside, f of our x sub k becomes the f of x, and then the more obvious little piece, the delta x, becomes the dx. So we want to do the same sort of thing down here. So we have the limit of the sum. So because of that, I'm going to write an integral. And they said the interval is from 0 to 1, so the integral will be from 0 to 1. The next piece is the function. So we have sine squared 2 pi xi. All we need to do there is replace the x of I star by x. So this becomes sine squared of 2 pi x. And then again, the last piece, I think the easy piece, this delta x becomes a dx. So there's the connection between the limit of the sum, limit of the Riemann sums becoming the definite integral. And again, just looking at the highlighting of the pieces, the limit of the sum is where we get the integral symbol. The 0 and the 1 depend on the interval we're working over. The function inside comes from the function that was inside of the sum, and we replace the delta x by a dx. So that's just practice with the notation. We still need to learn how to compute these things, but getting familiar with how the sum is connected to the integral is important, especially for the applications we do later on in Chapter 6. All right, so let's go ahead and continue on here and start learning how to calculate limits of Riemann sums. It turns out as we go to infinity, it doesn't matter whether we take the limit of a right, left, or midpoint Riemann sum, as they should all approach the same exact value. So what we're going to do is define our x sub k star. Since we could pick any value we want, left, right, middle, or otherwise, we're going to define x sub k star as a plus k delta x. That was the easiest version that we saw when we did left, right, and middle, and that happens to be the one for the right-hand endpoint. So even though you can compute these Riemann sums and the limits of these Riemann sums using left, right, or middle, we're going to do it using right-hand endpoints all the time, just because it's the easiest option. And then just a reminder that delta x is always equal to b minus a over n. Before we can jump in and actually compute our first definite integral, we're going to need some properties of summation notation and some formulas for specific sums that can help us get through the process. So let n be a positive integer, then the sum as k goes from 1 to n of some constant is going to just be that constant times n. Because if you think of about what's happening there, you just have the constant added to itself over and over again until you get n copies of that, because n is how many we're doing from 1 to n. Sorry, I wrote an n at the end because that was in my head. It's c all the way, but there ends up being n copies of that. So when you're done, this just ends up being the constant times n. So anytime you're taking the sum from 1 to n of some constant, you just get n times that constant. If you're taking the sum as k goes from 1 to n of k, so that would be like 1 plus 2 and so on up to n, what do you get for that one? So interesting little trick on this. Let's look at kind of like 1 to 100. If you take 1 plus 2 plus 3, and then you keep going, and you get to 99 plus 100 eventually. Now write it backwards. So this way you're going 1 plus 2 plus, and then going back to here, this would be 100, this would be 99, and this would be 98. And now if you take the sums vertically, you get 101 plus 101 plus 101 the whole way through. And you have n copies of that, or in this case, 100 copies of that. So the total of what we have so far is 100 times 101, but we have 2 copies of the sum we want, so to get the answer, we would divide that by 2. So the formula, notice there the n was 100 because we're adding up to 100. So the formula is n times n plus 1 over 2. And then we also have formulas for the sum as k goes from 1 to n of k squared given, and a formula for the sum as k goes from 1 to n of k cubed given. And these may seem all a little bit strange just sitting here in their own space, but when we turn the page, we're going to start trying to find a definite integral's value by taking the limit as n goes to infinity of some sums as k goes from 1 to n of functions. And sometimes those functions have constants inside, or a k squared, or a k cubed, and we need to be able to resolve those sums in order to find the limit. You'll see how that works on the next page. All right, we're going to go ahead and compute our first definite integral here. So use the limit definition to evaluate the integral from -4 to 2 of 2x plus 4 with respect to x. In order to set this up as a limit, we need to come up with a formula for delta x and for our xk star. So we'll start with that. So for delta x, we need to do b minus a over n, where b is the upper limit of the integration 2, minus a, which is the lower limit of integration -4, divided by n. And before we knew a value of n, because we were breaking it up into a certain amount of subintervals, in these types, we're not going to have n be a fixed number. It's going to be a variable, so it's going to stay there. The 2 negatives become a plus, so we get 2 plus 4, or 6 over n. So there's our delta x, and then we would need to come up with an xk star formula. So xk star is going to be the right-hand endpoint, and for that we start off with the lower limit, -4, and then we add k times delta x. So k times delta x, which is 6 over n. So simplifying this, making it easiest to plug into functions, this is 6k over n for the second term, and that -4 out front I'll put as a -4 on the backhand side. So that's just kind of a cleaner version to plug in. All right, so now let's see how the plugging in works. They want us to find the definite integral from -4 to 2 of 2x plus 4. So that 2x plus 4 is our function, and it's going to be with respect to x as a dx. So we're going to take the limit as n goes to infinity of the Riemann sum for our right-hand endpoint formula here. So we're going to take the sum as k goes from 1 to n of f of x k star times delta x. And now we just want to start plugging in and simplifying as much as we possibly can. So we have the limit as n goes to infinity is going to stay out front. The sum for now is going to stay out front. It will be our goal to eventually get rid of both of those pieces. But for now, what we're going to do is plug in. So the xk star is going to get plugged into our function. And this is our function, and this is our xk star. So it's going to become 2 times x, but in place of x, we're going to put our xk star. So 6k over n minus 4. That's just the 2x piece. I still need the plus 4 piece. So that takes care of f of xk star, and now I need delta x, but delta x is 6 over n. So now we've got it set up, and we want to just start trying to simplify it. So there's a few things that we want to note. One of them is, what's our variable in the sum? K is the variable in the sum. What's important about that is your delta x, 6 over n, does not have k in it. So that 6 over n can be factored out to the front. So let's do that next. We have the limit as n goes to infinity. And then out front of the sum, we'll write the 6 over n. And then we have our sum as k goes from 1 to n. And then I want to start simplifying what was inside here. So if I distribute, I get 12k over n. And then distribute here, we get a minus 8, 2 times negative 4, and then plus the other 4. And then these two are like terms, so we can combine those. So continuing on, we get the limit as n goes to infinity, and then we have our delta x out front, so that's the 6 over n. Then we have the sum as k goes from 1 to n. And then combining those two like terms, we have the 12k over n, which is already simplified, and the negative 8 and the plus 4 give us a negative 4. So now what we want to do is take that sum and distribute it to each of those two pieces and take any constants and factor them out. So this 12 and the n, which are constants in relation to the variable k, can be factored out of the sum. So let's see what all of that looks like. So we bring down the limit as n goes to infinity, and now we start thinking about stuff that's out front. We have the 6 over n, and then we're going to break the sums into two pieces. So on the first sum, I'm going to move the 12 over n out front, and then it's going to be the sum as k goes from 1 to n of k. Notice that's one of the things we had a special formula for on the previous page. So that's what we're trying to do, is get these sums to a place where we can just apply those properties from the previous page. The next sum is just of a constant, and we have a formula for that as well. So we can just leave that as a 4. I did take the negative and move it out front. All right, so now we apply those formulas and then simplify some more. So still a limit as n goes to infinity. The 6 over n is still out front. Going inside, we have the 12 over n. And then we have the formula for the sum as k goes from 1 to n of k is n times n plus 1 over 2. And then we also had a formula that said if you take the sum of a constant, you get that constant times n. So for this piece right here, we just get n times 4, so minus 4n. All right, so the sum is gone, and now we just have to take a limit. Almost there. So the limit as n goes to infinity, and then let's start distributing this back. So we're going to multiply this out so we have two pieces. And on the first piece, our constants up top, we have 6 times 12, and then we have n times n plus 1. And in the denominator of that one, we have, let's go ahead and highlight those pieces. we have this n, and that 2. So that would be a 2n squared in the denominator. And then minus the 4n over, well, the 4n times the 6n. So that's going to be minus 24n. And then that n on the bottom is still on the bottom. So what's going to happen with this limit? Well, remember back from chapter 2 when we were doing limits going to infinity, that if you were doing a fraction and the top and bottom had the same degree, you would just use the coefficients of that lead degree term. So if we were to look at our lead coefficients here, this is going to be an n squared, and this is going to be an n squared. So what are the coefficients on the top n squared? 6 times 12, and on the bottom one, it would be this 2. So the limit of that piece would just be 6 times 12 over 2, minus, on this one, it's easier, the n's cancel, and you just get minus 24. Doing a little bit more reducing, this 2 goes into that 6 3 times, so we end up with 3 times 12, which is 36, minus 24, which is 12. So the claim is the answer to that definite integral is 12. But it's a pretty messy process. We had to first come up with our delta x and our xk star, and then translate the integral into limit and sum notation, try and simplify that sum to the point where we could apply our rules. So when we got the sum as k goes from 1 to n, we were able to put in the n times n plus 1 over 2 piece. And over here we got to the sum of a constant, so we could multiply that constant times n. Once we did that, we're able to apply chapter 2 limit skills, and we come up with this answer. But is it right? We have a way to check. Let's try and do that exact same problem, but this time we're going to use geometry to evaluate the integral instead of using the limit of the sum. This is not an option that we have all the time, but it is an option available to us on this one, because as we do the limit from -4 to 2, we're finding the area between the function and the x-axis, with -4 as my left boundary and +2 as the right boundary. And we want the area between the graph and the axis, so we can go ahead and shade that in. We've got an area below the x-axis here, and an area above the x-axis here. And we're going to go ahead and find those two separately, and then we'll work it out. So this one I'm going to call area 1, and this one I'm going to call area 2, and both of those shapes are triangles. So we're just going to use the triangle formulas from geometry to find those areas. So area 1, being a triangle, it's going to be 1/2 times the base times the height. So that's 1/2 times whatever the base of A1 is. A1 goes from -2 to 2. So how wide is that? That's 4 units wide. And how tall is it? Here's the height of it. And if we take that height over to the y-axis, we see that's 5, 6, 7, 8 units high. So that's 1/2 times 4 times 8, which is 1/2 of, well, here, let's just do it this way. The 2 goes into 4 twice, and 2 times 8 is 16. So there's area 1. Now we find area 2, same exact strategy, 1/2 base times height. 1/2 base times height equals 1/2, and then this triangle goes from -4 to -2, so how wide is that? 2 units. How tall is it? 1, 2, 3, 4 is its height. So times 4, the 2's cancel, and we just get 4. So the area of the bigger triangle is 16. The area of the other triangle is 4. If you add those together, you get 20, and then you go, wait a minute, I thought it was supposed to be 12. But what you have to remember from previous sections is the concept of net area. That's what a Riemann sum calculates, is net area, and that's what definite integrals calculate, is net area. And so what we have to remember is that any areas that are below the x-axis, so we're talking about this area being below the x-axis, that would actually come out negative when it was in the definite integral. So the integral from -4 to 2 of 2x plus 4 with respect to x, or dx, would be a1, not plus a2, but minus a2. If we go back and look at the definition of net area, it says any areas that are below the x-axis, we subtract. And we do that because they would come out negative if we did them with a Riemann sum. So the area of the top one, 16, minus the area of the bottom one using geometry. And in geometry, you always get a positive area, so 4. And then we subtract those, and we get 12. So the geometry method matches up with the limit method. So the limit method doesn't look any more appealing, perhaps, but at least it seems to work. And I think given the choice, you'd say, I'm just going to use geometry to find these instead of the limit of these sums. But that only works when the area is a nice shape, and there's going to be lots of these we're going to do where the area is not a nice shape. So we're going to have to trust in that limit process and cross our fingers and hope later sections bring a cleaned up method. All right, let's go ahead and give this process one more try to get some more practice. So we're going to, again, use the limit definition to evaluate a definite integral. This time it's the integral from 0 to 5 of 1 plus 2x cubed with respect to x, or dx. So the first thing we want to do is find our delta x. So delta x is b minus a over n, where b is the upper limit of integration, minus a, the lower limit of integration, divided by n. And then we just simplify that, leaving the n in there. So that's going to be 5 over n. We need to come up with our x sub k star formula, which is going to always be using the formula a plus k times delta x. So a is your lower limit, which in this case is 0, plus k times delta x, which is 5 over n. So this one works out nice because the 0 goes away, so we just get 5k over n. So there's our x sub k star. All right, so now let's try to turn the definite integral into the limit of a sum. So the integral from 0 to 5 of 1 plus 2x cubed with respect to x, or dx, becomes the limit as n goes to infinity of the sum as k goes from 1 to n. And then we're supposed to do f of x sub k star. So we're supposed to take this function right here, and in place of the x value right there, we're going to plug xk star, which is that 5k over n. So this becomes 1 plus 2 times, and then instead of x, 5k over n, and then that's going to be raised to the third power, and then times delta x, and delta x is 5 over n. So there's the setup. Now we're going to try and simplify it like we did last time, to where we can apply some of our sum rules for our sigma notation, get the sigma out of there, and then evaluate the limit. So continuing on, so the limit as n goes to infinity. I'm going to factor the delta x out front because, again, reminder, the variable on the sum is k. That doesn't have a k in it, so it's a constant with respect to that summation, so it can be factored out front. And then we're going to want to try to split the sum. So we're going to take the sum of this piece and the sum of that piece. So we have the sum as k goes from 1 to n of 1, and then we want to pull out whatever constants we can, but I guess we'll wait on that for a moment. Let's just go ahead and split it up. So k goes from 1 to, not infinity, but to n. And let's see what we would have there. So, sorry about that. We have the 5 cubed, which would be 125, times 2. That would be 250. We have k raised to the third, and then we would have n raised to the third. The 5 over n we've already moved out front. So now what we want to do is start trying to apply some of our formulas. So we have the limit as n goes to infinity. We have the 5 over n. And now we have a piece we can apply the formula to. We have the sum of a constant, which is just that constant times n, so that would be 1 times n, or just n. And then on the next one, I'm going to factor out all of the non-k values. So k is our variable, so I can factor out the 250 and the n cubed. So I'm going to do that. So we have 250 over n cubed times the sum as k goes from 1 to n of k cubed. And then we have a formula for this piece on our previous page. It was one of the messy ones. It's not one of the ones we derived, but it is one that we have. So we're going to apply that. So we have the limit as n goes to infinity, 5 over n. I'm going to leave out there for now. We have the n plus the 250 over n cubed. And then we want to apply the formula for the sum as k goes from 1 to n of k cubed, which if you go back and look at the previous pages, that was n squared times n plus 1 squared over 4. So now let's go ahead and take this 5 over n and distribute that back into both pieces, and then we'll apply the limit and get our answer. So we have the limit as n goes to infinity. So distributing right here, the 5 over n with the n, we just get 5n over n. That's the clean piece. And then plus, what happens when we take 5 over n times all of this stuff? So we have the 5 times 250 would be 1250. And then in the numerator, we also have the n squared and the n plus 1 squared. And then in the denominator, we have the 4 from right here. And then we take this n times those 3 n's, and we'll get an n to the 4th in the denominator also. And then all of that, we want to take the limit of. So for the first one, it's pretty easy. The n's cancel, and we just get 5. On this piece, what you need to see is that we have a square here and an n, so that's an n squared, and then another n squared, so that's going to be n to the 4th in the top. And we also have n to the 4th in the bottom. So the limit for that fraction should just be the ratio of the two coefficients that we have there. So that should end up being 1250 over 4. So the first limit is going to be 5. The second part is going to be 1250 over 4. So this is equal to, sorry, let's get back to the blue. So this is equal to 5 plus 1250 over 4. The key is if the power on n is the same in the top and bottom, the limit as n goes to infinity is just the coefficient of that biggest power of n. So you don't have to actually expand the n plus 1 squared and do the FOIL and all that. You just need to realize that's going to be, let's look at it again. It's going to be an n squared from there, another n squared there, so that's n to the 4th and n to the 4th. So then at that point, you just take the coefficients, 1250 over 4 for your limit. And then you can go ahead and get a common denominator between those two. This actually, you can reduce here. 2 goes into 4 twice and into the top 625 times. The other one, you can multiply top and bottom by 2. And when you do all that, you get 10 over 2 plus 625 over 2. So 635 over 2 ends up being the answer for this definite integral. So it is quite a process. Definitely try some, come back, watch the video again if you need to. It takes some practice getting used to it. Just take it in stages. So you want to figure out your delta x, figure out your xk star, take the definite integral, rewrite it as the limit of the sum. Then you're trying to get those sums to a place where you know the formula, the sum of a constant, the sum of k cubed. Those are things we had formulas for in the previous page. Once you do that, you can get rid of the sums. Once you get rid of the sum, you can take the limit. And the limit part should be the easiest part, as long as you're paying attention to what is the power of n in the numerator and denominator. If it's the same, the limit as n goes to infinity is just the ratio of the coefficients, and that can speed you along. All right, let's go ahead and continue on. We're going to look at some properties of definite integrals and then do some easier stuff for now. And please just keep in mind that while the process of a definite integral is messy now, just like limits at one time were very messy and derivatives at one point were very messy, and then we started getting rules to make derivatives become better, the same thing will happen for the definite integral. But this is where they come from, and you need to understand where they come from clearly to do the applications we need to in Chapter 6. So just be patient and work through these limit of the Riemann sum problems slowly and carefully, and it will pay off for you in later chapters. All right, so let's look at these properties for definite integrals. Suppose f and g are any functions that are integrable on an interval containing a, b, and c, then what would be the integral from a to a of f of x? Well, since it's an area under a curve over a certain interval, if the boundaries match at a and a, you have no width. And if you have no width, you can have no area. So if the upper and lower limit are ever the same, then you end up just getting 0 for your answer. And then another one that is a little tricky to understand, I suppose, but comes in handy at times. If you take the limits, if they go from b to a and you switch them from a to b, that changes the sign of the integral. So if your limits get flipped, then you have to change the sign of the answer. Or, more commonly, if you want to flip the limits for some reason, you have to make sure you change the sign of the answer. You'll see where those come up in the problems on the next page. Some other properties that are more straightforward. If you're doing an integral of two functions added together, you can separate that into two separate integrals and then just add the results together so that you don't have to think about them at the same time. If there's a constant multiplying your function, you can just move that right out front. So constants can be factored out of the way when you're doing a definite integral. And then one last one, which is kind of a tricky one, but if you're doing an integral or two integrals and the upper limit of one matches the lower limit of the next, then you can just make it one integral by taking the lower limit of the first, the upper limit of the second, and making that the limit of the overall integral. And I want to go ahead and show you just a quick sketch of why that makes sense. So C doesn't necessarily have to be in between A and B, but I'm going to draw a picture where it is. So we're going to have A and B and some curve connecting them. So if I find the integral from A to B, I'm trying to find the area underneath that curve. Suppose there's some spot C in the middle. Then let's do some highlighting here. So the integral from A to C would be this area right here. And the integral from C to B would be this area right here. And the integral from A to B would be the whole thing. And we're saying that the whole thing from A to B is equal to the orange part plus the blue part. So that's the connection. So it's really just saying that you can break an integral into pieces at a middle boundary. This may seem strange, but we're going to end up using that a lot. And we tend to use it because we're doing a function that maybe goes something like this, and we're trying to find the area from here to here. And we want to know what is the actual area bounded between the function and the curve. But we know the definite integral treats areas below as a negative. So that spot where the function switches from positive to negative, we often want to let that be C and split the integral into two pieces so we can integrate and find the area for the part above the x-axis, and then the part below the x-axis we'll do separately. So you'll see that coming in future sections. All right, we're going to go ahead and end this section with some examples of using the rules that we just got on the previous page. And the good news is using those rule problems are easy. So we're going to have some homework problems that are short. They're not all going to be the limit as n goes to infinity of the sum as k goes from 1 to n and all of that mess that we looked at a couple times. There'll be some of that, but there'll be some of these as well, and they're easier. So let f of x and g of x be continuous on the interval from -4 to 3. Suppose that the definite integral from -4 to 3 of f of x dx is 5, and that the definite integral from -4 to 3 of g of x dx is equal to -2. Use that information to evaluate the definite integral from -4 to 3 of 2 times f of x minus 4 times g of x. So what we're going to do here is use a couple properties simultaneously. One of them is that you can split the integral up on the two separate pieces, and the other one is that you can factor constants out of integrals. So factoring the constant out of the first one, it becomes 2 times the integral from -4 to 3 of f of x dx. Then we move on to the second piece, factor the 4 out of the integral there, and say that's minus 4 times the integral from -4 to 3 of g of x dx. And then we know the answers for these integrals. So we know that the integral from -4 to 3 of f of x is 5, and we know that the integral from -4 to 3 of g of x is -2, so we can just substitute those values in. So we get 2 times 5 minus 4 times -2, so 10 plus 8, so 18. Nice and quick and easy. So there's our answer. Let's try some more. Suppose the integral from 0 to 1 of x cubed minus 2x dx is equal to -3/4. Then how about the integral from 0 to 1 of 2x cubed minus 4x? So what we need to notice here is that the inside piece of this one is the same as the inside piece of the one they gave us, except for a couple things. Actually, except for just one thing, there's a 2 there. So if we factor that 2 out to the front, that becomes the integral from 0 to 1 of x cubed minus 2x. Now the inside pieces are a match, and we know that that integral piece right here is equal to -3/4, so we can substitute that in place of the integral portion. Do a little bit of cancellation. This 2 goes into that 4 twice, and we end up with -3/2. Nice, quick, easy problem. Just trying to take the integral they give us and somehow recognize that in the integral we're trying to find. All right, so moving on to part B. So now when we look at the inside portion, 4x minus 2x, there's a 2 that's extra, just like before, but also it's been reversed as well. So we'll take this in a couple steps. First, we'll take the 2 out. So we're going from 0 to 1 of 4x minus, we took the 2 out, so this would be 2x minus x cubed. So now the issue is the inside piece is not written in the same order that it was up above. But remember, you can reverse the order of a subtraction by factoring out a negative. So I'll factor a negative out front with the -2. That reverses what's inside. It becomes x cubed minus 2x. Now the inside matches what they gave us up top. So we can substitute in and say that that integral is -3/4. We end up with the same multiplication we had a minute ago, except for this time it's a negative times a negative. So this time we end up with +3/2 instead of -3/2. All right, just a couple more. So evaluate the integral from 1 to 0. Okay, so that's not what we were given. We were given 0 to 1, so those limits need to be reversed. So to do this, we need to remember the property that says if you take the limits of integration and you reverse them, so again, looking carefully at the order, this was 1 to 0, and now I've changed it to 0 to 1. If you're going to do that, that changes the sign of the answer. And then the inside piece would still be 2x minus x cubed, but that 2x minus x cubed inside here is reverse of what we had before. So I want to turn that around. Turning that around, reversing these two, comes from factoring out a negative. If I factor out a negative, when there's already a negative out front, the two negatives make a positive out front. And this gets flipped around to x cubed minus 2x. Now we have an exact match of our beginning integral that they gave us. So our answer is going to be negative 3/4. All right, one final one, and this has to do with that idea of splitting. So if we're going to go from 0, evaluate the integral from 0 to 3 of x cubed minus 2x dx minus the integral from 1 to 3 of x cubed minus 2x. So what we want to do is combine these into 1. To do that, you need the upper limit of 1 to match the lower limit of the other, and that's not happening right now. We have a 3 and a 1. If you look at the other two limits, it's a 0 and a 3, so we do not have the match we want. But what if I took these two and I switched their order? Then the 3 would be on the bottom, and then it would match. So that's what I'm going to do. I'm going to copy the first one. So integral from 0 to 3 of x cubed minus 2x dx. And then I'm going to switch the limits of integration on the other one, put the 1 up top and the 3 on the bottom. But if you do that, it changes the sign. So what was a negative becomes a positive. And then it's x cubed minus 2x dx. But now we've got the match that we were looking for. We have the upper limit here matches the lower limit there. When that happens, you can make this and this your new upper and lower limits and just have it be a single integral. So this would go from 0 to 1 now of x cubed minus 2x dx, which, is that the one they gave us? The one they gave us was x cubed minus 2x. That's a match. So what was the answer up there? Negative 3/4. So that's the answer down here as well, is negative 3/4. So there's some examples of using the property. By the way, if you want to just like argue this from an area point of view, if you take the area from 0 to 3 and subtract out the area from 1 to 3, what should be left over is the area from 0 to 1. See if we got room to do a quick visual on that. So you have some function. You're going from 0 to 3. You find if you take all of that area, and then you subtract away the area from 1 to 3. So subtract that out with my eraser. Then what's left is the area from 0 to 1. So that's what they had us do there. They took the area from 0 to 3. They subtracted the area from 1 to 3. And what did we end up with? The area from 0 to 1, which was the one they gave us at the top. So we were able to plug in that number. All right, that wraps up section 5.2.